It's easy to think of an electrical circuit as simple plumbing. You connect a battery to a light bulb, and direct current flows from point A to point B, like water moving smoothly through a clear pipe. In this simple model, the only thing slowing the electricity down is standard resistance, a static, predictable restriction to the flow, much like a narrow section of that pipe. But send a high-frequency, fast-changing digital pulse down that exact same copper wire, and the physics shift completely. The energy doesn't flow smoothly anymore. The fast signal is delayed, the crisp edges of the pulse warp to the soft curves, and some of the electrical energy actually ricochets backward toward the source. When you increase the speed of an electrical signal, the wire stops behaving like an empty pipe. It awakens hidden physical forces, creating a complex environment that requires an entirely different framework to understand: impedance. The first of these hidden forces is inductance. Because every wire creates a small magnetic field, the circuit physically resists any sudden changes in the flow of current. The second force is capacitance. Conductors store electric charge, so when voltage tries to instantly drop or spike, that charge fights back to keep it stable. Combine these two opposing forces and you get reactance. It is the dynamic opposition to any changing electrical signal. In a basic direct current circuit, the voltage and current hold perfectly steady. The magnetic and electric fields remain completely still, which is why we spend most of our lives safely ignoring these forces. But when the signal fluctuates, reactance wakes up and combines with standard resistance. This combined total is impedance, a single value that represents the complete, multifaceted environment the signal has to fight through. How severe that impedance becomes depends entirely on one variable: the frequency of the signal. When a slow wave rolls through a circuit, it glides past the inductance with almost zero pushback. But accelerate into a high-frequency pulse, and the fields cannot keep up. The inductive reactance scales up, turning into a massive physical barrier that chokes the signal. Because this alternating opposition causes the voltage and current to physically shift out of step with one another, the two forces don't point in the same direction. They act at a 90-degree angle to each other. To calculate the total combined effect, engineers treat resistance and reactance as the two sides of a right-angled triangle, using the Pythagorean theorem to solve for the hypotenuse, the final impedance. Since impedance reacts dynamically to the speed of the signal, a wire that flawlessly carries power to your desk lamp can act as a hostile blocking wall to high-speed computer data. We can see this problem across an entire system. This diagram illustrates a transmission line with its own characteristic impedance, Z0. The conflict happens at the boundary. When a signal reaches a destination with a radically different impedance, like ZL here, they violently clash. This graph shows the resulting physics. When the forward voltage step hits that mismatched boundary, the load cannot absorb all the energy. The excess has nowhere to go but violently backward, generating the distinct negative reflected wave you see returning nanoseconds later. This unabsorbed, bouncing energy echoes back and forth along the wire. In high-speed digital networks, this reflection causes destructive ringing that corrupts the ones and zeros, completely ruining the data. Engineers cannot eliminate impedance. It is a permanent mathematical reality governing alternating current and high-frequency design. Instead of fighting the physics, they control it through a central engineering practice known as impedance matching. The goal is to align the entire system. If the source, the transmission line, and the terminating load are all perfectly tuned to share the exact same impedance, the boundary effectively disappears, dropping the reflection coefficient to zero. In this zero reflection state, the circuit achieves maximum power transfer. The digital pulse completes its journey with its integrity completely intact. Every high-speed signal effectively transforms its conductor into a complex, high-stakes environment. Controlling impedance is how we dominate that environment, ensuring that the digital pulses we send arrive with perfect clarity.